Hello, we're going to talk about basic concepts of probability and counting. At this time, go ahead and pause the video to write down the objectives in question style. Instead of reading all these definitions, I'm going to give you a general idea. An outcome is what you're trying to figure out in the probability experiment. Sample space is all the possible outcomes, and let's look at the first example to get an idea of what each definition represents. Survey consists of asking people for their blood types, including whether they are Rh positive or negative. Determine the number of outcomes and identify the sample space. A tree diagram would be a great strategy to do this. When doing the tree diagram, we're going to have the blood types first, and then each blood type can either be positive or negative. So notice at the bottom of this tree, we have all the possible outcomes. The sample space will be written as brace each possible outcome and then an end brace. Part of the question was how many, so include that there's 8 possible outcomes. A simple event is whenever you only have one outcome. For example, when you're tossing heads and rolling a 3 on a die, we can see through the tree diagram this happens once. This is a simple event. Let's say you want to toss heads and roll an even number. Because this has multiple outcomes, it is not simple, as you can see in the tree diagram as well. So each event listed in these examples, we're going to figure out how many outcomes there are and then explain whether it's simple or not. So for quality assurance, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So the sample space would be either defective or not defective. Then event A is strictly just looking at defective parts. Because that's only one outcome, this is a simple event. You can pause the video to write that down. If we were to look at rolling a 6-sided die, and event B is rolling at least a 4, the sample size would be 4, 5, or 6. So because it has more than one outcome, it is not simple. Fundamental counting principle means if you have events in a sequence and there's a different amount of ways for each, you can multiply their number of ways to figure out the total number of ways events can happen in sequence. So for example, we have this new car problem. You've got different manufacturers, car sizes, and colors. And how many different ways can you select one of each? We're going to draw a tree diagram. So the fundamental counting principle just says, hey, multiply the number of ways, or multiply the 3 manufacturers, the 2 sizes, and the 4 different colors, 24. But then I want you to also draw in this tree diagram to show that when you count that very last row, you get 24 different ways. The access code for a car's security system consists of 4 digits, and each digit can be any number 0 through 9. Realize that that is 10 options. So how many access codes are possible when each digit can only be used once and not repeated? Each digit can be repeated, and each digit can be repeated, but the first digit can't be 0 or 1. When I do any problem, I like to mark out how many sequence or how many events are going in a row. So I'm putting out 4 underlines to mark the 4 digits for this code. Each digit can only be used once and not repeated. How many options do you have for the first digit? We've got 10. Once that digit is used, then we only have 9 options for the next position. Now that those 2 digits are used and we can't repeat them, the next position would be 8 and so on. We multiply them to figure out, to see the total amount of ways. 500 or 5,040. How many ways if each digit could be repeated? That means we have 10 options for the first, 10 options for the second, 10 options for the third, and so on, giving us 10,000 as a result. So what if the first digit can't be 0 or 1? Well, then that means we only have 8 available. After that, though, anything can be repeated, so we have 10 for the rest of this, giving us 8,000 ways. Diving into types of probability, we've got your classic probability. That's how we use classic probability for what is the probability of getting a heads when you flip a coin, where you take the number of outcomes in the event you want, divided by the total number of outcomes in the sample space. This is based on theory. So let's roll a 6-sided die. You're going to find the probability of rolling a 3, rolling a 7, rolling a number less than 5. Down below at the bottom of your screen, you see our sample space. So when we ask how many outcomes does a 3 happen, that's only once out of 6 total. So there's the probability for the first one. How many times do you see in our sample space rolling a 7 exists? Well, it doesn't. So 0 out of 6, which means you would just say that that's 0 probability. Rolling a number less than 5, so less than, there are 4 options out of 6. Let's reduce that though. So I would be okay if you wrote 2/3 instead of 4/6 at this last one. Go ahead and pause if you need more detail for your notes. Empirical probability is when you actually do an experiment, and we take the number of times you actually have successes divided by the total amount of times you did the experiment. Go ahead and pause the video so you can read the example. If I only want the number of print books, I look at that number divided by how many people took the survey. So 560 divided by 1,502, and reduce or write it as a decimal. So about 37% is what we're looking at. Go ahead and pause the video to read their next example. With a frequency distribution, we're going to take the, how many is in the event of what we want divided by the sample size. Because we want ages from 25 to 34 years old, we're looking at 765 divided by the total 3,000, which is about 25%. This is a review just to let you know that whenever an experiment's repeated over and over and over, the empirical probability eventually approaches the classical or the theoretical probability of an event. The last type of probability is subjective. That's whenever you've got an educated guess happening. So let's run through these types. We're going to classify the statement as either classical, empirical, or subjective and explain our reasoning. Probability you're going to get an A on your next test is 90%. It's probably subjective. There's no data to back you up, and we don't know how many tests you've taken and what your average is before that. Probability that a voter chosen at random will be younger than 35 years old is 3/10. We can get that data. So this would be empirical, easily done with a survey. When you know that a raffle's been going on and there's 1,000 tickets and the probability of winning is 1 out of 1,000, that's theory. So there's classical probability. So there's a scale for probability. It's always between 0 and 1 inclusive. 0 meaning impossible, 1 meaning it's guaranteed to happen, and you see the other options if you're between. So the complement of an event is denoted as E prime, or E with an apostrophe, and it's assumed that an event happening and the complement to that, so the event not happening, will always add to be 100%, or 1. Let's use it from that last example. Let's find the probability selecting a social networking site user who's not 25 to 34. So we already know previously that we got 765 out of 3,000 for being 25 to 34. So we could take 1 minus 765 over 3,000. Getting us this probability of, oh, there's a typo, hold on. Never mind, not a typo. So you can take 1 minus the probability of that event happening to get the end result. Let's explore using a tree diagram. Let's say you're tossing a coin and spinning the spinner that you see on the screen. We're going to use a tree diagram to find the probability of each event. Take time in your notes to draw the entire tree diagram of what you see up here, and realize that the first event is what's the probability of getting a tails and an odd number. And you see the circling pieces that there are 4 out of a total of 16. Using that same tree diagram, we're going to go on to the next problem. Probability of tossing a head or spinning a number greater than 3. So that includes any head, there's 8 there, and then number greater than 3, add them all up together, we've got 13 out of 16 as a probability. Let's go with your college ID number. You've got 8 digits. What's the probability of getting your college identification number when you randomly generate 8 digits? These digits can be repeated, so let's set up 8 lines to represent your code. Realize that you've got 10 items for the first, and you can repeat digits, so that's 10 times itself 8 times. This is the total amount of ways. So that would be in the denominator of this probability. Now we got to figure out, well, what's the, how many ways can you guess correctly? There's only one right way you can guess correctly. So this is a 1 out of 100 million of a chance. And you can see the resulting decimal here at the bottom. Thank you for watching.